So this time, we're going to talk about two things really, neutralization reactions and the common ion effect. So neutralization, these are reactions you talked about in Chem 131 when you thought about an acid reacting with a base. In Chem 132, so far, we've only thought about how an acid or a base reacts with water. And now we're going to think in terms of equilibrium about what happens when an acid reacts with a base. And so we can kind of think about four different neutralization scenarios. We have a strong acid that reacts with a strong base. And when you have an equal amount of each of those, your solution is going to be neutral because the acid just cancels out the base. When you mix a weak acid with a strong base, if you mix equal amounts of them, you're going to end up with a basic solution. Whereas if you mix equal amounts of a strong acid and a weak base, you're going to end up with an acidic solution. And so you can think about that you have sort of more of the strong component than you have of the weak component in terms of the amount of OH minus or H3O plus that's produced. So that's how we get that pattern. If you mix a weak acid and a weak base, then the chemistry gets a little bit messy. And whether you end up with a basic or an acidic solution at the end depends on the relative values of the Ka and the Kb. In any case, we can define Kn as the equilibrium constant for a neutralization reaction. And so a neutralization reaction is going to follow the pattern you saw in Chem 131, where you have some acid plus some base becomes water and a salt. Okay, so here's a neutralization reaction. Let's classify this. So in order to classify this, we want to look at the reactants. We see that HNO2, that's going to be a weak acid. How do we know? Well, we see that it's an acid because it has an H, and we know it's not one of our strong acids. HNO3 is a strong acid, but HNO2 is a weak acid. Then we look at our base, and so our base here, OH minus, is a strong base. We don't have the ion, the potassium or sodium or whatever it was, because we think about that the NaOH has already fully dissociated, and it's really the OH minus that is acting as the strong base, and whatever that counterion was, it was just a spectator. So here we have a weak acid reacting with a strong base, so that makes a weak acid strong base titration. Okay, so let's find the Kn value for this reaction based on Ks we already know. So we know that Ka for HNO2 is 4.5 times 10 to the minus 4. Now the Ka reaction is that HNO2 reacts with water to form H3O plus, because it's an acid, and NO2 minus, the conjugate base. So that's Ka. To get from the Ka reaction to our neutralization reaction, we need to end up with OH minus on the reactant side and with water on the product side. But here we have water on the reactant side, H3O plus. So what we're going to do is we're going to add another reaction that's the autoionization of water, but we're going to reverse the direction. So we're going to look at H3O plus OH minus becomes 2 waters. Okay. Now, if it goes 2 waters become H2O plus and OH minus, that is Kw. But this is the reverse of that. So recall that if you reverse the direction of the reaction, you find the inverse of its equilibrium constant. And so you see if we add those together, we get our neutralization reaction because, look here, the H3O pluses cancel, and one of the waters cancels. And so we end up with HNO2 plus OH minus becomes H2O, water, plus NO2 minus. Okay, and we talked about before that if we add reactions, we multiply their equilibrium constant. So that would be Ka times 1 over Kw, or Ka over Kw. Ka is, in this problem, we said is 4.5 times 10 to the minus 4. And if we divide by Kw, 10 to the minus 14, then we see that the Kn value here, kind of ran out of room. So Kn ends up being 4.5 times 10 to the 10th power. This is a very large K. So that means that this neutralization reaction basically goes to completion. And so we find that that's true generally when you have a strong plus a weak or a strong plus a strong neutralization reaction. Those have very large Kn. So Kn is much, much greater than 1. And so those basically go to completion. Okay. So changing topics a little bit here. Why does adding lithium fluoride to a solution of hydrofluoric acid raise the pH? So let's think about how hydrofluoric acid can affect the pH. We can write out the Ka equilibrium for this reaction. And if we add lithium fluoride, that is a source in this case. Lithium fluoride is a source of F- ion. So if we add extra F- ion, we're increasing the concentration of a product. And so that is going to drive the equilibrium toward the reactants. So adding more F- is actually going to decrease the amount of H3O+. Okay, so if we decrease H3O+, that is going to increase the pH. Okay, so that raises the pH. And that's because, so if we think about our options, the lithium ion is basic, so OH- concentration increases, no. Addition of Li plus removes F from the solution, no. Addition of F- ions shifts equilibrium toward HF, that is true. Because the solution is aqueous, water can be both an acid and a base, true, but not helpful here. So the answer here is that if you add an ion that is part of the pH determining equilibrium, it's going to change the pH. We call this the common ion effect. So it's a shift in equilibrium upon addition of a substance that provides more of an ion already in solution. And this is just an application of Le Chatelier's principle. So in this case, if we added more product, the conjugate base, then that would cause the equilibrium to respond by producing more reactants, the acid form, which would decrease the amount of H3O+ in solution. And we can imagine other variants on this. So you want to remember that Le Chatelier's principle still applies to acid-base reactions, even because these are still equilibrium processes. Okay, similar thing. How would you expect the pH of 0.4 molar NH3 to change if 0.1 mole of NH4Cl is added? So let's first start by writing the reaction of what happens when NH3 is in water. And think about how that's going to influence pH. So the pH is influenced by the Kb reaction of ammonia. Okay, and so if we add more NH4Cl, NH4Cl is a salt, so it's going to dissociate into NH4 plus and Cl minus. NH4 plus, look, is one of the components in our reaction. So if we increase the amount of NH4 plus, we're going to see a shift in the reaction toward the reactants. Okay, that's going to cause a reduction in the amount of the other product, OH minus. So if we decrease OH minus, that is going to increase H3O plus. Okay, because those still have to multiply together to be Kw. And so that is going to cause a decrease in pH because increasing H3O plus decreases pH. So the correct answer is decrease. And now we can quantify that scenario. So if the pH of a 0.4 molar solution of NH3 is 11.43, what would be the pH if you added 0.1 moles of NH4Cl to a 0.5 liter solution? Okay, we know that the pH should decrease, but let's find out how much. We're going to use that same Kb reaction. And since we're quantifying concentrations at equilibrium, we're going to need an ice table to organize our thoughts. Okay, so there's our Kb reaction. We know that Kb equals 1.8 times 10 to the minus 5. And so we're using our pattern of a base plus water becomes the conjugate acid and OH minus. And so let's think about our initial concentrations. Our initial concentration of NH3 in this scenario is 0.4 molar. Water doesn't matter. We get us NH4 plus from the 0.1 mole of NH4Cl that's added. There's a 1-to-1 relationship between moles of NH4Cl and moles of NH4 plus, and the whole volume is 0.5 liters. Okay, so that means that the initial concentration of NH4 plus is going to be 0.2 molar. The initial concentration before this goes to equilibrium is basically 0. And so because of that, we're going to imagine that this reaction proceeds in the direction of the products. Okay. And so it's going to be 0.2 plus x and x. And so we can fill all of that into our Kb expression, where we're going to have the concentration of NH4 plus, which is 0.2 plus x, times our concentration of OH minus, which is just x, divided by the concentration of NH3, 0.40 minus x, and all of that is going to equal 1.8 times 10 to the minus 5. Okay, here we can make our small x approximation twice. So we can assume that 0.2 plus x and 0.40 minus x are both just equal to the number, that x is small compared to those values. And so that leads us with that we have 0.2x divided by 0.4 equals 1.8 times 10 to the minus 5. And so if we rearrange that and solve for x, we find that x equals 3.9 times 10 to the minus 5. Let's check our assumption. Yeah, if we subtract 3.9 times 10 to the minus 5 from either 0.20 or 0.40, we end up with the same number. So our assumption was valid. Okay, if this is our x, what were we trying to find again? Oh, right, the pH. So our OH minus concentration we found is equal to x, so that's 3.9 times 10 to the minus 5. That's OH, so if we want to find H3O plus, we can use Kw divided by OH minus. So that's going to be 10 to the negative 14 divided by 3.9 times 10 to the minus 5. So the H3O plus concentration will equal 2.56 times 10 to the minus 10. And if we find the pH, that'll be negative log of that number. The pH will be 9.59. Okay, so before we said that the pH would decrease if we added NH4Cl. And look, we see that it decreases by about 2 units.